Okay, thank you, Chris and Nick, for organizing this conference and for inviting me. Let me start by saying that I'm among those physicists that think that philosophers have an important role to play in this game. Among others, is to prevent us from redefining what it means to understand something. Sometimes we do that kind of thing, and you should be there keeping us honest. Okay, so the subject I'm going to talk about involves collaboration with many people. I will not be naming every individual one because we have very little time. And I'm going to start. Oh, I should have said also that I'm supposed to be the what was the word?
The radical?
The radical, and I don't know why, because I very much agree with everything that was said before, almost everything, except a little detail. I do believe that we should take quantum mechanics as seriously as a theory that applies not only to ensembles but also to individual systems. Otherwise, we will have a very serious problem if we want to talk about our universe, the unique universe to which we have access, and then for quantum cosmology and things of that sort would not make sense. So, let me remind everybody, in this audience probably is obviously absurdity, but let me remind anyway, that we have a very serious problem in quantum theory. We have a problem, the measurement problem, the fact that we have two different evolution equations, one evolution when the system is left unperturbed, and a different evolution when we measure an observable. And of course, when we consider the measuring apparatus and the observer and everything else as part of the system, the quantum mechanical system we want to describe, it's not clear how to put this together. Although, of course, there are many proposals, among them the many word interpretations, and I will tell you why I feel none of them are adequate. Of course, many other people have said this. Well, the point is then, what should determine what kind of evolution should things follow? This is what Roger Penrose calls the U process, and this is what he calls the R process. And we have been very influenced by his notion, his idea that when we put quantum theory together with general relativity, perhaps it's inadequate to just try to modify GR into the setting of quantum theory and leave quantum theory alone. Perhaps both should be modified. And moreover, in that modification, one should resolve the measurement problem, because if gravity is brought into the picture and that doesn't help you in this direction, then it's not clear what could. Moreover, we know that trying to apply quantum theory directly with to GR, at least in a straightforward manner, produces a series of problems. We know that everybody knows, and it has mentioned already here, the problem of time in canonical quantum gravity. There are several proposals to resolve it, but let me not get into that. We also know about the information loss paradox. And the question is, could these two very big issues be perhaps resolved by this idea, by following Penrose's proposals that modifying quantum mechanics in order to resolve the measurement problem should be a necessity of putting relativity and quantum mechanics together? Well, we have done some little thought about this idea, and some ideas suggest a positive answer. It has been done with Elias, and it's in this place, we just uploaded it a few months ago. However, the point I'm going to talk about here is connected with something else, which is the measurement problem and cosmology. As you know, nowadays, inflation is supposed to be a fundamental aspect or a central aspect of modern cosmology. And one of the great success stories is the emergence of fluctuations during the cosmological era that represents perhaps the unique situation we have available in which general relativity, quantum mechanics, and observations come together. There is no other situation, and I want you to see the observations because these are actual pictures of what we want to talk about. So, for those of you that are not involved in cosmology, this is more or less, this picture has already been appearing here. These are our current understanding of the history of our universe. Here we have our satellite that is looking at the deep past in a universe populated with galaxies that is now accelerating. Here we see the moment in which, according to our understanding, the first stars lit up. And here is the most ancient light that we can see in the universe that is depicted in that map of what the CMB sky looks like. And here we go back to the inflationary regime, and where these quantum fluctuations coupled to gravity are supposed to seed the emergence of all structure that we have in the universe today. So let me quickly take you through the inflationary story. The basics is that the basic idea is that from some generic state that emerged after the Planck era, inflation will drive you very quickly to something that is basically a flat Robertson-Walker spacetime whose method is described in this way. The advantages is that it resolves some of the naturalness problems that afflicted standard Big Bang cosmology before that. But the most important success of this scheme is that they produce, out of quantum fluctuations, these seeds of cosmic structure. We see these seeds in the CMB, and the analysis of data and of the theory matches beautifully. It's perhaps one of the big success stories of current physics. But let's consider carefully what does this mean. How exactly, from quantum mechanical uncertainties of a quantum state, which is completely homogeneous and isotropic, do actual inhomogeneities arise? This question, of course, is connected with the measurement problem in quantum mechanics, and I'm going to say a little bit more about that, but let me continue for a moment telling you about how this analysis is done. So one starts from a theory in which you have gravity coupled to a scalar field, this famous inflaton field. One considers a background solution, which is the space-time I was describing, in which the scale factor depends only on this time parameter, as well as the scalar field that depends also on this time parameter. Einstein equations basically tells us that under those conditions the universe will be controlled by something that is very roughly a cosmological constant, so it will span exponentially, and the scalar field satisfies a similar equation for which the slow roll condition, in which basically you have something like the force being equated to being equal to the dragging force, reaches some kind of steady state solution. That solution is an attractor of the dynamical equation, so one believes that even if one doesn't start in exactly that situation, one would rapidly arrive to something of that sort. And please, the equations are just more for guidance than for everything. Don't pay attention to all the details. Well, on top of that background, one considers perturbations. One considers modifying the scalar field by adding some little piece that depends on position, and modifying the metric a little bit by adding also something that depends on position as well. I'm going to consider here one particular kind of perturbations. There are more, but that's not important. And then one describes these perturbations in terms of some new variables and proceeds to quantize these new variables. Simply writes a quantum field theory for those variables, and then evaluates the two-point function, the two-point correlation function on that state, and from that thing one obtains the famous power spectrum. This state on which one is evaluating the two-point function is the Banch-Davis vacuum, which, as I said, is completely homogeneous and isotropic. So we have a state that is, at the quantum mechanical level, homogeneous and isotropic, even though it has some uncertainty in the values of the fields at any position. The observations are basically a measurement of the temperature and isotropies. These points in the sky are cooler and these ones are hotter. This is a map of the tools of the celestial sphere in microwaves after the galaxy is removed, which is that thick red band that you see in the map that I circulated. And that is supposed to come, that's supposed to be, those anisotropies are supposed to be the result of the Newtonian potential that makes these photons have lose more energy than these photons when they are traveling towards us. The temperature at which all the photons were emitted was basically the ionization temperature of hydrogen, and the temperature is reduced to around 2.7 Kelvin due to the cosmological expansion, and then there are, so this part is homogeneous and isotropic, but the small fluctuations are associated with the Newtonian potential, that perturbation of the metric that I described there, at the surface of flash scattering, the surface at which these photons were emitted. People then take this map, decompose it into spherical harmonics, and one can write then an expression for what is this coefficient alpha Lm in terms of this Newtonian potential. This is the Newtonian potential at the point of emission, and the spherical harmonics just to obtain this particular coefficient. And people focus on this quantity, which is the average over orientations of the square of the quantity. When they do that, they obtain a fantastic good agreement of theory and observations. However, if I look at something else, at this quantity, which is the quantity that is directly measured and that is directly extracted from that globe that I just told you, and I compute the expectation value of this quantity, I get 0. So why should I trust this prediction and not this? People will tell you all sorts of things, that quantum mechanics should not be applied to individual systems, quantum mechanics should be applied. Then you ask, why couldn't we apply it to the universe, therefore? Well, they say, well, you have to take an ergodic position that says, well, ergodicity requires some type of equilibrium. The universe is certainly not equilibrium, and moreover, refers to a system that is allowed to go over all positions in phase over time, and we're certainly looking at the universe at one particular time, and then they will tell you perhaps we need to identify averages over time with averages over orientation and things of that sort. We don't trust any of that stuff. We want a theory that tells us exactly what we see and that makes predictions that we can trust in all situations. Moreover, I want a theory that explains to me how and when did the anisotropies in the universe emerge. When did they arose? Well, as I said, there are many answers. Some answers say, well, look, this is a standard quantum mechanics. We just measure, and when we measure, things use Copenhagen interpretation. The problem is that that our own existence is part of what cosmology should explain. So I should not be able to rely on my existence and presence here as being the cause of the generation of the inhomogeneities that would lead to galaxies to form and eventually stars to form and me to eventually be born to do these things. Well, correlations, people say, well, there are correlations. Of course there are correlations, but the correlation does not imply a breakdown of the symmetry. It's very easy to see that. Decoherence, many world interpretations. Well, you know what? I'm going to go through this at the end when people ask questions. So I'm going to jump because I know I have to be careful with time. And we are convinced that none of the known physics resolves this problem. None of the known physics can resolve the problem, and if none of the known physics can do it, we need new physics. And as I said, this is, well, when we say new physics, one has to be careful when you talk about new physics. Well, why is this new physics arising there and not anywhere else? Well, as I said, this is the only situation in which the combination of these three things come to play that we have available today. So it wouldn't be surprising that new physics arose or was seen for the first time in that context and not in others. We won't an explanation of the emergence of structure that as a physical process taking place in time. Why is that? Because I take the word emergence in this context as at least to refer to something that was not there initially being there later. That's the emergence in the, cosmological context. So what do? We propose to follow, inspire on these ideas of Penrose. We propose to add to the inflationary paradigm a spontaneous dynamical collapse of the quantum state to take us from the homogeneous and isotropic situation that inflation was supposed to drive us into something that doesn't have that property. So the collapse, a spontaneous collapse of the wave function can take you from a state that has symmetry to a state that doesn't have symmetry. And that's what we will try to do. So how you do that? Well, there are various approaches. Here, I'm going to tell you about one, our latest idea, which is to take something called the CSL. This is a theory that was developed by Philip Pearl as a generalization of the GRW proposal, which is basically a collapse theory, spontaneous collapse theory, but that is happening continuously. That's why it's continuous spontaneous localization. I should say collapse theories have been considered for a long time, recently by Weinberg as well. This theory contains of two things. Basically, a modified Schrödinger equation, which after integrating it, involves a change in the evolution which is controlled by an extra term besides the standard Hamiltonian evolution. And this extra term is composed of two things. An operator that tells me towards which kind of states does the collapse try to drive a particular a generic state of the system, a parameter controlling how intense this effect is, and a stochastic function or a random function of time. And for and the second rule, called the probability rule, telling us how to compute the probability of the realization of each particular stochastic function. This theory was designed to unify, at least in the level of non-relativistic quantum mechanics, the U and R processes. So this single equation will combine the unitary evolution and the reduction processes. The unitary evolution you will have when this is the dominant part of the equations. Of course, we will have small corrections, and the reduction process will take place basically when this becomes the dominant term, even though this guy is also acting. I shouldn't say, I don't have too much time to go over this, but there's a history of work here, and they even have estimated what's the value of the parameter when they assume that the position operator is somehow the preferred observable, of the preferred quantity towards which states tend, and they estimate the value that is of the order of 10 to the minus 16 seconds to make sure that on the one hand, type tests of quantum mechanics at the atomic and molecular level are not disrupted by this term, and on the other hand that the chair is always in a state of relatively well-defined position, and it's never in a state of superposition of them being here. For doing that kind of analysis, they estimate the value of this parameter. How am I doing? I'm doing fine. Yes.
Talk for 20 minutes.
Okay. So our approach, we will try to adapt this to situations involving quantum fields and gravitation. As we saw, dynamical reduction of a quantum state requires the notion of time. Collapses take place in times. So, as quantum gravity has a problem of time, and its resolution generically involves somehow passing to a sort of semi-classical regime, we will be assuming that one can rely on the semi-classical framework, even though we recognize that at the deepest levels, the theory should be a quantum theory of gravity. So in this sense, I'm going to be very close to what James just told us, try to modify the theory the least, but to try to guide myself by by what the some degree of some consistency of the proposal and the data, which is something which we value very, very much. So our point of view is that this emergence of of classical GR from some underlying quantum gravity phenomena will not only lead to general relativity, but will contain traces of the quantum regime that are reflected by this dynamical state reduction. So at the effective level where I have recovered time and space-time, there will be left from the quantum gravity regime this thing that looks like the quantum gravity, like the dynamical reduction, again following the ideas of Penrose and Diossi. It's natural to expect that if any of this is going to work, will require the curvature scales to be much smaller than the Planck scale, and therefore inflation should fall within that regime, because it's supposed to be happening at the gut scales, which is much smaller than it's a scale that is smaller than the Planck regime. Yes.
Can you go back first?
Yeah.
So the deepest level of gravitation must be quantum mechanical in nature. You just mean unmodified ordinary quantum mechanics, just like
no, I don't know. I would take it should be quantum mechanical. There should be quantum mechanical degrees of freedom that perhaps are not even geometric, as we have heard. I don't know what they are.
But it's not modified quantum mechanics.
Perhaps it's also modified quantum mechanics.
Okay.
I don't know what unmodified quantum mechanics means in a regime where you don't have time. So, in some sense, it needs to be modified. Okay? But I'm not going to take a stand there. My stand is going to be that the equations that I'm going to write, my position is that the equations that I'm going to write should be taken as a sort of hydrodynamical description of gravity, and not the fundamental description of gravity, because the theory that I wrote has a very serious problem that does not allow me to take it completely seriously. And by the way, it's a problem. Okay, let me show what the problem is. Okay, so I do the same stuff as before. I take a metric and consider background, consider these perturbations, which are called the Newtonian potential. This is the only part of the metric that may depend on the position. And I start the system at eta equals to minus t with tau, minus tau, with tau is a very large number. This is the inflationary regime. It's necessary for simplicity, it's convenient to take the value of this eta parameter running on the negative, running into the positive direction, but in the negative part of the real axis. And the scalar fields must be treated. The scalar field will be treated as in quantum field theory in curved spacetime, in that curved spacetime, and we will use the semi-classical gravity, but modified by the collapse of the wave function. So these states will be able to collapse. The state will not follow simply the evolution dictated by the Hamiltonian, but will follow this evolution dictated by the CSL theory. And the problem is that during that modification makes this quantity not conserved. And since this quantity is not conserved, this equation cannot hold. That, by the way, is exactly the same problem that happens to stochastic semi-classical gravity when you consider individual system. In that case, when you consider average over ensembles, the average of the stochastic variable has zero value, but each individual realization does not, and each individual realization will have the same problem as we. So we cannot take this as fundamental. We take this as a good approximation with things to be developed further. Okay, so we will be concentrated in the modes other than the zero mode, which are responsible, the zero mode is responsible for the overall inflationary expansion of the universe, and the non-zero modes are the ones that are responsible for this structure, these anisotropies and these inhomogeneities. So at the early state, we have at the early stage when after inflation has run for a little bit, the state is described by the Banks-Davis vacuum, which is, as I said, 100% homogeneous and isotropic. And in fact, the vacuum state, the operators are these operators, the field operator and momentum conjugate operators, are characterized by wave functions that are centered at zero and have certain uncertainties. The collapse will modify the quantum state, and generically, the expectation values of these quantities will no longer be zero. They are zero in the Banks-Davis vacuum. Okay, so now we will apply this CSL theory, which involves these stochastic functions, and it's very important that we take the view that our universe is controlled by mode by a stochastic function and corresponds to a single realization of the stochastic functions for each k. So our universe is not an ensemble of universes. It's one universe among an ensemble of conceivable universe, and the stochastic function is just selected, is one of them selected from there. Well, now we write the semi-classical Einstein equation that I wrote before. Takes this form, connecting the Newtonian potential. I have gone to the Fourier transform description. So the Newtonian potential, the K, the mode K component of the Newtonian potential is controlled by the expectation value of the momentum conjugate of the field. That quantity at the start, if the state of the field is the vacuum state, is zero, and therefore the Fourier transform of the Newtonian potential is zero. Therefore the Newtonian potential is zero, and our universe is homogeneous and isotropic. It's only when the state of the field jumps to something else that the universe will not longer be homogeneous and isotropic. If I knew exactly how the state jumped, I would be able actually to compute the Newtonian potential at every point, and therefore I would be able to compute the difference in temperature between that particular point and the mean according to this equation. And given this difference, this temperature fluctuation, I will be able to compute this parameter alpha Lm, which has this particular expression. And as I said, there is no analogous expression that appears in the standard procedures. In the standard procedure, if you try to write an equation like this, you would obtain zero, and you would say, I cannot trust that prediction. I'm speaking too fast. Okay. Now, but this quantity is controlled by stochasticity. These quantities I don't know, because each one of them is controlled by a stochastic function. And stochasticity means I cannot predict it. So, but the point is that when I see what this quantity is, I see that it's a contribution of many modes. So it's like a sum. This quantity is a sum of many complex numbers. Each one of these quantities is a complex number. So it's a sum of complex numbers, of many complex numbers. Well, actually here, infinite number of complex numbers. So what we have, and this part has a stochastic aspect. So what we basically have is a random walk. The evaluation of this quantity is a random walk. It's a random sum of complex numbers, or a random walk in a complex plane. For a random walk, you of course cannot hope to predict what its value is going to be, but you can predict what is the most likely value of its magnitude. So you compute the magnitude, and now you have an expression. And this expression differs from the standard expression in that we have the vacuum expectation value here in each one of these quantities, rather than the expectation value of the product. So this is very important. You want the expectation value here because you know that it has come from this quantity, and you want this quantity not to be different from zero to generate actual inhomogeneities. Okay. But now you say, I will want to compute now the most likely value of this quantity. One can do that by going to, for example, consider an ensemble of random walks and computing the mean value of this quantity. And by that, by doing that, one obtains an expression. And the important thing is that this function f of k will have to have a particular type of behavior as a function of k in order to produce the data that we know fit well with that map that we have there. So that I'm going to use to get clues about what is this fundamental collapse theory, what is this CSL, what should be the version of CSL that can fit the data. Let me go now by mode by mode, and consider what is the operator A driving the collapse and what should be the parameter, the value of the parameter lambda. It's convenient to work with these rescale fields, rescaling the scalar field and rescaling the momentum conjugate, and put everything in a box to avoid delta functions and things like that. And now we need to compute what is the value, the expectation value, the square of the expectation value of this quantity P average over the ensemble. Again, it's very important that this quantity is what should be computed and not this one. Because this one would be non-zero even if the space-time is homogeneous and isotropic. This one will not. When we take the collapse operator being the momentum conjugate to the field, it turns out that we get this particular form of the spectrum. But this form of the spectrum is not what we need to recover the data that we see here. It should be basically proportional to k and not to k squared. In order to adjust the theory to fit the data, I need to assume that this parameter is not universal, it's not the same for each mode, but has this particular form. That has the added virtue of giving now a correct dimensionality to the parameter. And if I do that, then I get basically the spectrum that I know that will work, plus small corrections. So these corrections are a prediction of this particular version of the theory applied to the setting. I could, in principle, take the data and start constraining the value of the, see if these values are allowed or not allowed. Okay? As so far, the problem is that the data that we have so far are not precise enough to rule out these particular values. If we adjust this term, if we assume that this is the dominant term and that it fits and that is adjusted to fit the data. We have done a similar consideration now, assuming that what is collapsing is the field rather than its momentum conjugate, and we get something similar but with a slightly different type of corrections. Again, it's something similar, but here again, the dominant term doesn't go like k. If I need it to go like k, I need to again assume that the parameter is dependent on k, and this again gives the correct dimensionality to this parameter. If I assume this, then I get again a term that goes like k, that I'm going to assume is the dominant term, plus small corrections. When I adjust this to the data and using the values of the inflaton potential, assuming that the inflation is occurring at the granularification scale, one obtains a value for this parameter, sorry, this should be lambda tilde, which is 10 to the minus 19 seconds, and that's only 3 orders of magnitude away from the prediction that was, for the order of magnitude estimate that was selected to fit particle physics, quantum mechanics in the lab, and predict the existence of the rapid localization of macroscopic objects. So this is the GRW suggestion for the value of this parameter.
This is with the scalar field as the collapse operator.
Yeah, well, for both of them, you get the same. You see these expressions? This expression is the thing that has to be matched to the and they are right, equal, and that part of the expression is the same in the two. What is different in the two schemes is the form of the corrections. Okay?
Thank you.
It may be that these corrections, if you ask me to bet, I would bet that these corrections, if we go and measure carefully enough, will not fit the data. It would be very lucky for us to have guessed what the correct theory is. But my point is different. My point is that one has here the opportunity to take data and start constraining these kind of theories and learning which ones may and which ones may not work. Once one has something that works, one may then try to connect to models of quantum gravity that are deeper down. So in some sense, following James' advice, start close to things that you know, things that you have data for, make this additional step, and then hope to learn how to walk into a deeper place faster. Okay. These collapse operators look very strange. Very strange. This particular this dependence of the collapse parameter on the mode number sounds very strange. It can easily be seen to be equivalent in collapsing, instead of the scalar field, into this modified, this version of the scalar field, which has this extra operator here, Laplacian squared to the power 1/4 acting on the quantum operator. When we rewrite this in this form, then the evolution equation, the CSL evolution equation, looks very nice. Now the parameter is just a universal parameter, but the field that is collapsing, controlling the collapse, is something strange. I think this is a clue. I don't know what it's a clue of, but I think it's what it indicates. But I think it's a clue of what is the thing that is fundamentally driving the CSL theory, if I think of it as a fundamental theory. If I think of CSL as a fundamental modification of quantum mechanics, it should not be, there should be an operator there that is unspecified, and that it should be, that I can specify differently in different situations. It should be some universal operator that controls everything in all situations. So we know that a position is something that seems to be preferred in laboratory experiments, and to avoid the churn of being a superposition of being there and here. And on the field level, when applied to fields, it seems to be something like this. What it is that joins these two things together, we don't know. Perhaps something like the Weyl square to some power or something of that sort. We don't know. Let me just say. But this is what I think is a clue that we should start learning from. Something similar happens when I do it in the collapse operator in the momentum. Also there is these operators now to the -1/4. So why should these be the operators? As I said, I have no idea, but I think there is a clue there that it would be very interesting to study. And as I said, they should be determined by the fundamental theory of CSL, considered as a truly alternative version of quantum mechanics, valid for all possible systems and in all circumstances. What this theory is, we don't know. We have taken a step into exploring it in this particular situation, which, as I said, is a very unique situation, which should be taken advantage of. So a little bit of propaganda here, other studies that we have done. One direct prediction of the scheme, at least in this semi-classical approach that we have used, is that there are no so-called tensorial modes. There should not be tensorial modes in the CMB, and these tensorial modes, at least at the first order in perturbation theory, they may appear at the second order, but those will be extremely reduced and not observable, at least for a foreseeable future. There are various things that can be considered. We have considered theories in which were not continuous collapses, but single individual collapses, one for each mode or many for each mode. There are predictions of this type of analysis for the study of non-Gaussianities, and this is something that is we hope to get into this, because this is something very, very interesting that this can be now extracted from current data in Planck. Well, let me finish here and let me have some questions.
Can you say a bit more about the fine-tuning? Because what you presented was along the lines of the particular simple inflation model. So
yes, we have applied this in a very, very simple model, basically phi squared. It should be applied to others. We have not gone into that direction. All the inflationary models have this problem, that you start from an homogeneous anisotropic state and you're supposed to generate the anisotropies. Which one is the correct inflationary potential, or if there should be more than one inflaton? We haven't gone into that direction, but it's something that should be done, of course.
There's a question back there.
So, in this cosmological example, it seems like the reason why you need to modify quantum mechanics, if I understood correctly, is because you have this Bunch-Davies state as your initial state for inflation.
Yes.
But there are some quantum gravity theories that you see which predict like you can have like a non-Bunch-Davies initial state, something like a Bogel transform or something. Can that avoid this problem?
The ones that I know of are all have the same feature. They are not Bunch-Davies, but they are nevertheless homogeneous anisotropic. So if you start with any other of those states, I mean, if you modify, for example, the dynamics, if you put the potential, change the potential, then the state will quickly evolve into something that is not the Bunch-Davies. If inflation is not exponential, but you have corrections, then the state will not. But that does not change the fundamental aspect that we need to resolve, which is how you break the symmetry. And nothing, if your state is symmetric and your dynamics is symmetric,
Time for one last question, Chip?
Yeah, I just want to make sure that I sort of am taking away the right thing from this. So if you start with the CSL dynamics for collapse and you use position operator, that's going to make predictions for what you would see in the CMB.
Yes.
If you started with the Bunch-Davies vacuum. And you're saying that what we see refutes that, and you have to have a different operator governing the collapse.
That's
You've
right.
given one option for what it is.
Yes.
So that's using cosmological constraints to figure out what the collapse mechanism is and how it works.
that's right. That's what I think we should do.
That's
Yeah.
exciting.
Okay, on that note, please join me in thanking Dan.